which numbers are smaller than others, which words come first in a dictionary, which people share a birthday. All three questions are really the same question. This chapter gives you one simple tool that answers all of them. Hello and welcome. Let's start this chapter together. It is about relations. A relation is an easy idea. It tells us which things go together. For example, which numbers are less than other numbers. We learn what a relation is and its main properties. We see two ways to draw a relation, and we study two special kinds of relation. Take your time. Each idea builds on the one before it. This is the plan for the whole chapter. First, relations and their properties. Then NRE relations. Those are not in these slides yet. Next, how to represent relations. After that, closures of relations, also not in these slides yet. Then equivalence relations. And last, partial orderings. Let's start with the first topic. Now we turn to the first topic, relations and their properties. We learn what a relation is and the main properties a relation can have. This is the plan for this section. First, we compare relations with functions. Then we study the properties of relations. We look at reflexive relations. Then symmetric and antisymmetric relations. Then transitive relations. At the end, we learn how to combine two relations into a new one. Let's start with the main definition. A binary relation R from a set A to a set B is a subset of a cross B. That means R is just a set of ordered pairs. Each pair takes one element from A and one element from B. Now let's fix a relation to work with. The set A is 0, 1, 2. The set B is MB and R holds four pairs, 0, a 0B, 1A, and 2B. Remember these four pairs. On the next slide we draw them. These are the same four pairs drawn as a picture. An arrow goes from each first element to its partner. 0 has two arrows. 1 has one arrow. 2 has one arrow. The table shows the same four pairs. A cross mark means that pair is in R. Now the point of this slide. A relation is more general than a function. In a function, each element of A points to exactly one element of B in a relation. An element of A may point to many elements or to none. Look at 0. It points to A, and it also points to B, so this relation is not a function. Often the two sets are the same. A binary relation R on a set A is a subset of a cross A. So both parts of each pair now come from the same set A. Now a small example. Let it be the set of B. See then R holds three pairs, a B, and a C. Every one of those pairs uses only members of A, so R is a relation on A. Let's list the pairs of a relation, one step at a time. The set is 1, 2, 3, 4. We say A is related to B when it divides B. That means B is a whole number of copies of A with no remainder. We take each first number in turn. Start with 1. 1 divides every number, so 1 gives four pairs, 1, 1, 1, 2, 1, 3, and 1, 4. Now 2. 2 divides 2 and 2 divides 4. 2 does not divide 3, so 2 gives the pairs 2, 2 and 2, 4. Now 3. Inside our set 3 divides only 3, so 3 gives one pair 3, 3. Last 4. 4 divides only 4, so 4 gives the pair 4, 4. Altogether we found 8 pairs. Now a counting question. A set A has n elements. How many different relations can we build on it? We start with the thing we want to count. the number of relations on A. Step 1. A relation on A is nothing more than a subset of across A, so counting relations is the same as counting subsets of across A. Step 2. There is a rule for subsets. A set with m elements has 2 to the power m subsets, so the answer is 2 to the power, the size of across A. Step 3. How big is across A? It is n times n, which is n squared, so the answer is 2 to the power n squared. Let's try it. If it has 3 elements, we get 2 to the power 9. That is 512 relations on a set of only 3 elements. These 6 relations on the integers are our test cases for the rest of the section. We come back to them again and again, so let's read them slowly. R1 holds the pair of B when it is less than or equal to B. R2 holds a B when it is greater than B. R3 holds a B when it equals B, or it equals minus B. R4 holds a B when it equals B. R5 holds a B when it equals B plus 1. And R6 holds a B when a plus B is less than or equal to 3. One more thing about all 6. The integers form an infinite set, so each of these 6 relations is itself an infinite set of pairs. We can never list them all. We test them instead. Let's test one pair carefully. We take the pair 1, 1 and we try it in every rule. The method is always the same. Put a equal 1 and b equal 1 into the rule, then see if the statement is true. R1 asks, is 1 less than or equal to 1? Yes, so the pair is in R1. R2 asks, is 1 greater than 1? No, so the pair is not in R2. R3 asks, does 1 equal 1 or does 1 equal minus 1? The first half is true, so the pair is in R3. R4 asks, does 1 equal 1? Yes, so the pair is in R4. R5 asks, does 1 equal 1 plus 1, that is 2? No, so the pair is not in R5. R6 asks, is 1 plus 1 less than or equal to 3? 1 plus 1 is 2 and 2 is at most 3. Yes, so the pair is in R6. Altogether, the pair 1, 1 sits in R1, R3, R4, and R6. Now we run the same test on 4 more pairs. The pair 1, 1, which we just worked out, sits in R1, R3, R4, and R6. The pair 1, 2. 1 is less than 2, so it is in R1. And 1 plus 2 is 3, which is at most 3, so it is in R6. The pair 2, 1. 2 is greater than 1, so it is in R2. 2 equals 1 plus 1, so it is in R5. And 2 plus 1 is 3, so it is in R6. The pair 1 minus 1. 1 is greater than minus 1, so it is in R2. 1 equals minus 1, so it is in R3. And 1 plus minus 1 is 0, so it is in R6. The pair 2, 2. 2 is less than or equal to 2, so it is in R1. 2 equals 2, so it is in R3 and in R4. But 2 plus 2 is 4, which is more than 3, so it is not in R6. Let's learn our first property. It is called reflexive. A relation R is reflexive when every element is related to itself. That means the pair is in R for every element in the set A. So the test is easy. Walk through the elements one by one. Ask, is this element related to itself? If even one element fails, the relation is not reflexive. One special case. If the set A is empty, then the empty relation is reflexive. There is no element to check, so it passes for free. We call that vacuously true. Now we test all 6 relations. For each one we put B equal to and see what the rule says. R1 becomes A is less than or equal to A that is true for every number, so R1 is reflexive. R2 becomes A is greater than A that is never true. Take 3. 3 is not greater than 3, so R2 is not reflexive and 3 is our witness. R3 becomes A equals A or A equals minus A the first half is always true, so R3 is reflexive. R4 becomes A equals A always true, so R4 is reflexive. R5 becomes A equals A plus 1. Take 3. 3 is not equal to 4, so R5 is not reflexive and 3 is the witness. R6 becomes A plus A is at most 3. Take 4. 4 plus 4 is 8, and 8 is more than 3. So R6 is not reflexive and 4 is the witness. Now the symmetric property. A relation R is symmetric when the pairs work in both directions. If the pair of B is in R, then the pair B must also be in R. So build this habit. To break symmetry, you only need one bad pair. Find a pair of B that is in R where the flipped pair B is missing. That one pair is your witness, and it settles the question. Let's check all 6 for symmetry. R1 is less than or equal to B. Take the pair 3, 4. 3 is less than or equal to 4, so that pair is in R1. Now flip it. Is 4 less than or equal to 3? No. So R1 is not symmetric, and the pair 3, 4 is the witness. R2 is greater than B. Take the pair 4, 3. 4 is greater than 3. Flip it. 3 is not greater than 4. So R2 is not symmetric, and 4, 3 is the witness. R3 equals B or equals minus B. If it is plus or minus B, then B is plus or minus A. The rule reads the same both ways. So R3 is symmetric. R4 equals B if A equals B. Then B equals A, so R4 is symmetric. R5 equals B plus 1. Take the pair 4, 3. 4 equals 3 plus 1. Flip it. 3 does not equal 4 plus 1. So R5 is not symmetric and 4, 3 is the witness. R6 plus B is at most 3. Adding does not care about order. A plus B equals B plus A, so R6 is symmetric. Next is the antisymmetric property. Be careful with this one. Antisymmetric is not the opposite of symmetric. A relation can have both properties and it can have neither. Now the rule. If the pair XY is in R and the pair YX is also in R, then X and Y must be the same element. So you may never have two arrows running between two different elements. A simple example. If A is less than or equal to B and B is less than or equal to A, then A and B must be equal. To break the rule, find two different elements that point at each other. That pair is your witness. Now we test all 6 against the antisymmetric rule. R1. Suppose A is at most B, and B is at most A, then A and B must be equal. So R1 is antisymmetric. R2. Suppose A is greater than B, and B is greater than A. That can never happen at the same time. So the rule is never broken, and R2 is antisymmetric. R3. Now a counterexample. The pair 1 minus 1 is in R3 because 1 equals minus 1. And the pair minus 1, 1 is also in R3, but 1 is not equal to minus 1. So R3 is not antisymmetric, and that pair of pairs is the witness. R4. If A equals B and B equals A, then of course A equals B, so R4 is antisymmetric. R5. Suppose A equals B plus 1 and B equals A plus 1. Put them together and you get A equals A plus 2, which is impossible. So the rule is never broken, and R5 is antisymmetric. R6, another counterexample. The pair 1, 2 is in R6 since 1 plus 2 is 3. The pair 2, 1 is also in R6, but 1 is not equal to 2, so R6 is not antisymmetric. Now the transitive property. This one chains pairs together. If the pair XY is in R and the pair YZ is in R, then the pair XZ must also be in R. So any two steps that join must have a direct shortcut. For example, if it is at most B and B is at most C, then it is at most C. Let's work that out for R1, which is less than or equal to. Suppose the pair of B is in R and the pair BC is in R. Step 1. By the definition of R1, that means A is at most B and B is at most C. Step 2. Chain the two together. Then A is at most C, so the pair of C is in R, the shortcut is there, so R1 is transitive. Let's test all 6 for transitivity. R1, if A is at most B and B is at most C, then A is at most C, so R1 is transitive. R2, if O is bigger than B and B is bigger than C, then O is bigger than C, so R2 is transitive. R3, each step either keeps the number or flips its sign. 2 steps still leave you at plus or minus C, so R3 is transitive. R4, if A equals B and B equals C, then A equals C, so R4 is transitive. R5, now a counterexample. The pair 3, 2 is in R5 since 3 is 2 plus 1. The pair 2, 1 is in R5 since 2 is 1 plus 1. Chain them. We would need the pair 3, 1, but 3 is not 1 plus 1, so R5 is not transitive. R6, another counterexample. The pair 2, 1 is in R6 since 2 plus 1 is 3. The pair 1, 2 is in R6, 2. Chain them. We would need the pair 2, 2, but 2 plus 2 is 4, which is more than 3, so R6 is not transitive. A relation is just a set of pairs, so we can combine two relations the same way we combine sets. We can take the union, the intersection, and the two differences. Let's fix the two relations we will use. The relation R1 holds 3 pairs, 1, 1, 2, 2, and 3, 3. It matches each number with itself. The relation R2 holds 4 pairs, 1, 1, 1, 2, 1, 3, and 1, 4. It matches 1 with everything. Notice that the pair 1, 1 is in both. Remember that. It is the only pair the two relations share. Now we work the 4 operations. The union keeps every pair that is in either relation. So we take all 3 pairs of R1 and all 4 pairs of R2, and we write the shared pair 1, 1 only once. That gives 6 pairs. The intersection keeps only the pairs that are in both relations. The only pair in both is 1, 1, so the intersection has just that single pair. The difference R1 minus R2 keeps the pairs of R1 that are not in R2. We drop 1, 1 because it is in R2. That leaves 2, 2 and 3, 3. The difference R2 minus R1 keeps the pairs of R2 that are not in R1. Again, we drop 1, 1. That leaves 1, 2, 1, 3, and 1, 4. Now we learn composition. It joins two relations through a shared middle set. The relation R1 goes from set A to set B. The relation R2 goes from set B to set C. The composite of R2 with R1 is written R2, small circle, R1. It goes all the way from set A to set C. Now the rule, and it works both ways. The pair XZ is in the composite exactly when there is some Y in B with the pair XY in R1 and the pair YZ in R2. Nothing else is in the composite. so we use y as a stepping stone. We go from x to y, then from y to z if no such stepping stone exists. The pair xz is not in the composite. Let's set up a composition we can see. The set A holds a B, and C the set B holds M, N, O, and P the set C holds W, X, Y, and ZR1 holds the pairs of P and B, MR2 holds the pairs MW, MX, and NZ. The picture shows 3 columns of dots. R1 draws the arrows from it to B, 1 arrow from it to P, and 1 from B to M. R2 draws the arrows from B to C, M to W, M to X, and N to Z. On the next slide we walk the paths and read off the composite. Now we find the composite. We look for paths that cross both columns of arrows. Start at B, the arrow BM takes us to M from M. The arrow MW takes us to W, both steps exist, so the pair BW is in the composite. Still a B from M, there is a second arrow, MX, that takes us to X, so the pair BX is in the composite too. Now try A, the arrow, a P takes us to P, but P has no arrow leaving it in R2. The path stops there, so it gives us nothing. And C, there is no arrow leaving C at all, so C gives us nothing either. So the composite, R2 circle R1, holds exactly 2 pairs, BW and BX. We can also compose a relation with itself. That gives us its powers. We define them step by step. The basis step, r to the power 1, is just r itself. The inductive step, r to the power n plus 1 equals r to the power n, composed with r, so r squared is r composed with r cubed is r squared composed with r. Now a useful fact. Theorem 1 says the relation r is transitive if, and only if r to the power n is a subset of r, for every n equal to 1, 2, 3, and so on. In plain words, a transitive relation never gains new pairs when you raise it to a power. The proof uses mathematical induction, and you can find it in the text. Now we turn to a new section, representing relations. So far we wrote a relation as a set of pairs. Now we learn 2 other ways to show one, a grid of zeros and ones, and a picture with dots and arrows. This is the plan for this section. First, we represent relations using matrices. A matrix is a grid of zeros and ones. Second, we represent relations using digraphs. A digraph is a drawing with dots and arrows. Let's start with matrices. A relation between 2 finite sets can be shown with a matrix of zeros and ones. Let the relation R go from a set A to a set B. Write the elements of A as a 1, a 2, and so on. Write the elements of B as B1, B2, and so on. We build a grid called M sub R. The rule is simple. The entry in row I in column J is 1 if the pair A sub I, B sub J is in R, it is 0 if that pair is not in R. So each 1 means these 2 are related, and each 0 means they are not. You may list the elements in any order you like, but when A and B are the same set, use the same order for the rows and the columns. Let's build a matrix from scratch. The set A is 1, 2, 3. The set B is 1, 2. The relation holds the pair of B when it is bigger than B. We take the rows in the order 1, 2, 3, and the columns in the order 1, 2. Before we draw the grid, we list the pairs. Start with the equal one. Is 1 bigger than 1? No. Is 1 bigger than 2? No. So 1 gives us no pairs at all. Now a equal 2. Is 2 bigger than 1? Yes. Is 2 bigger than 2? No. So 2 gives us 1 pair, 2, 1. Now a equal 3. 3 is bigger than 1 and 3 is bigger than 2. So 3 gives us two pairs, 3, 1 and 3, 2. The relation holds 3 pairs in total. Now we fill the grid, one row at a time. Row 1 stands for the value 1. The pair 1, 1 is not in the relation, so we write a 0. The pair 1, 2 is not in the relation either, so we write another 0. Row 1 is 0, 0. Row 2 stands for the value 2. The pair 2, 1 is in the relation, so we write a 1. The pair 2, 2 is not, so we write a 0. Row 2 is 1, 0. Row 3 stands for the value 3. Both pairs, 3, 1 and 3, 2, are in the relation, so row 3 is 1, 1. Put the 3 rows together and you get the matrix. Notice the shape. A 1 appears wherever the row value is bigger than the column value, so the ones sit below the diagonal. Now we go the other way. We are given the matrix and we must find the pairs. The set A has 3 elements, so there are 3 rows. The set B has 5 elements, so there are 5 columns. A pair is in the relation whenever its entry is 1, so we hunt for every one in the grid, row by row. In row 1, there is a single one and it sits in column 2, so the pair A1, B2 is in the relation. In row 2, there are ones in columns 1, 3, and 4. So we get 3 pairs, a 2B1, a 2B3, and a 2B4. In row 3, there are ones in columns 1, 3, and 5. So we get a 3B1, a 3B3, and a 3B5. Collect all 7 pairs, and that is the relation R. When the relation R lives on a single set A, the rows and the columns stand for the same elements. So the matrix is square. Its shape tells us the property of R. First, reflexive. A relation is reflexive when every element is related to itself. In the matrix, the main diagonal runs from the top left corner to the bottom right corner, so every entry on that diagonal must be 1. Second, symmetric. A relation is symmetric when a related to be forces be related to A in the matrix. The entry in row I column J equals the entry in row J column I, so the matrix looks the same when you fold it along the diagonal. Third, antisymmetric. For 2 different elements, you may never have both mirror entries equal to 1. So when I is not equal to J, at least one of the 2 must be 0. These are the 3 shapes, side by side. A dot means the entry does not matter. The first matrix is reflexive. Look at the diagonal. Every entry on it is 1. The rest of the grid can be anything. The second matrix is symmetric. Row 1 column 2 is 1, and row 2 column 1 is 1. Row 1 column 3 is 0, and row 3 column 1 is 0. Every mirror pair matches, so the picture is the same if you fold it along the diagonal. The third matrix is antisymmetric. Look at each mirror pair again. Row 1 column 2 is 1, so row 2 column 1 must be 0, and it is. All the ones sit on one side of the diagonal. This relation is given only by its matrix. It is a 3 by 3 grid of zeros and ones. Let's read it out loud. Row 1 is 1, 1, 0. Row 2 is 1, 1, 1. Row 3 is 0, 1, 1. The question is, which of the 3 properties does this relation have? Is it reflexive? Is it symmetric? Is it antisymmetric? We check them one at a time on the next slide. Each check has a fixed recipe, so nothing here is guesswork. Now the 3 checks. Reflexive. Look along the main diagonal from the top left to the bottom right. The entries are 1, 1, 1. Every diagonal entry is 1, so the relation is reflexive. Symmetric, compare each mirror pair. Row 1 column 2 is 1 and row 2 column 1 is 1. They match. Row 1 column 3 is 0 and row 3 column 1 is 0. They match. Row 2 column 3 is 1 and row 3 column 2 is 1. They match too. So the relation is symmetric. Antisymmetric. Here we look for a mirror pair where both entries are 1 on two different elements. We find one straight away. Row 1 column 2 is 1 and row 2 column 1 is also 1, and 1 is not equal to 2. So the relation is not antisymmetric, and that mirror pair is the witness. This is the second way to show a relation. It uses a picture called a directed graph, or digraph for short. A digraph has two parts. The first part is a set of dots called vertices. The second part is a set of arrows called edges. Each edge is an ordered pair of vertices. For the edge of B, we draw an arrow from it to B. The vertex A, where the arrow starts, is the initial vertex. The vertex B, where the arrow ends, is the terminal vertex. Sometimes an edge goes from a vertex back to itself. An edge of the form is called a loop. In the picture we have 4 vertices and one arrow for each pair in the relation. Look at the edge BB, it is a loop, a little circle at the vertex B. This time we are given the picture, and we must find the pairs. The method is simple. Take the vertices one at a time and follow every arrow that leaves them. Start at vertex 1. 2 arrows leave it, 1 to 3 and 1 to 4. So we get the pairs 1, 3 and 1, 4. Now vertex 2. 3 arrows leave it, 1 goes to 1. 1 is the loop, a little circle back to 2 itself, and 1 goes to 3. So we get 2, 1, 2, 2, and 2, 3. Now vertex 3. 2 arrows leave it. 1 goes to 1, and 1 is a loop back to 3. So we get 3, 1, and 3, 3. Last, vertex 4. 2 arrows leave it to 1 and to 3. So we get 4, 1, and 4, 3. Remember, each loop gives a pair where a vertex points to itself. The picture also lets us check the 4 main properties by eye. First, reflexivity. A relation is reflexive when there is a loop at every single vertex. If even one vertex has no loop, the relation is not reflexive. Second, symmetry. A relation is symmetric when every arrow has a matching arrow going back. So if there is an arrow from X to Y, there must also be an arrow from Y to X. Third, antisymmetry. A relation is antisymmetric when no two different vertices point at each other. Fourth, transitivity. A relation is transitive when every two-step path has a direct shortcut. So if there is an arrow from X to Y and an arrow from Y to Z, then there must be a direct arrow from X to Z. Learn these 4 checks, and you can name the properties of any digraph. Let's read a digraph and then name its properties. This graph has 4 vertices. B, C, and D look for the arrows. There is only one. It is a small circle at the vertex A that is a loop, an arrow that goes from a vertex back to itself. So the relation holds exactly one pair. The pair A, the vertices B, C, and D take part in nothing at all. On the next slide, we check the 4 properties against this one pair. Now the 4 checks against the single pair A. Is it reflexive? No. Reflexive means every vertex has a loop. Vertex B has no loop, so the pair BB is missing. That is our witness. Is it symmetric? Yes. The only pair is A, flip it, and you get A again, which is in the relation. So nothing is broken. Is it antisymmetric? Yes. The rule only matters when two different elements point at each other. Our only pair is a loop, so the 2 elements are the same. The rule holds. Is it transitive? Yes. The only chain we can build is followed by A that needs the pair A to be present, and it is. So the shortcut is there. This is a second digraph. Again, there are 4 vertices. Follow the arrows. One arrow goes from A to B, one arrow goes from B down to D, and one arrow goes from D back up to B, so B and D point at each other. That gives 3 pairs, a B, B, D, and D, B. Look carefully for loops. There are none. No vertex points back at itself. Remember that because it settles the first property straight away. Now the 4 checks for this graph. Is it reflexive? No, there are no loops at all, so the pair A is missing. Is it symmetric? No. There is an arrow from A to B, but no arrow from B back to A, so the pair B is our witness. Is it antisymmetric? No. Antisymmetric forbids 2 different vertices from pointing at each other, but B and D do exactly that. The pair BD and the pair DB are both in the relation, and B is not equal to D. Is it transitive? No. Follow B to D, then D back to B. That is a 2-step path from B to B, so we would need a loop at B. There is no loop at B, so the shortcut is missing. This is a third digraph, again with 4 vertices. Follow the arrows. One arrow goes from A down to C, the other goes from C up to B. So the relation holds 2 pairs, a C and CB. Notice something important. The first arrow ends at C, and the second arrow starts at C, so the 2 arrows join head to tail. That means we can walk a 2-step path, from A through C to B. Remember that when we test transitivity. Again, there are no loops, and vertex D takes part in nothing. Now the 4 checks for this graph. Is it reflexive? No, there are no loops, so the pair A is missing. Is it symmetric? No. There is an arrow from A to C, but no arrow from C back to A. That pair is our witness. Is it antisymmetric? Yes. We only have 2 arrows. Check each reverse. The reverse of a C is CA, and that is not in the relation. The reverse of CB is BC, and that is not in the relation either. So no 2 different vertices point at each other. Is it transitive? No. Walk from A to C, then from C to B. That is a 2-step path from A to B, so we would need a direct arrow from A to B. There is none. The shortcut is missing. This is a 4th digraph, again with 4 vertices. Follow the arrows. One arrow goes from A down to C, the other goes from B down to D. So the relation holds 2 pairs, a C and BD. This time the 2 arrows never touch. The first one ends at C, and no arrow starts at C. The second one ends at D, and no arrow starts at D, so we can never walk a 2-step path, and there are no loops. Now the 4 checks for this graph. Is it reflexive? No, there are no loops, so the pair A is missing. Is it symmetric? No. There is an arrow from B to D, but no arrow from D back to B. That is our witness. Is it antisymmetric? Yes. Check the reverses. The reverse of a C is CA, which is not there. The reverse of BD is DB, which is not there either. So no 2 different vertices point at each other. Is it transitive? Yes, but in a trivial way. To break transitivity, we would need 2 arrows where the first one ends where the second one begins. Here that never happens. Nothing to check means nothing can fail. We say the rule holds vacuously. Now let's compute the powers of a relation, step by step. This is the relation R. It holds 4 pairs. A to B, B to C, C to D, and D back to B. The picture shows the same 4 arrows. Look at the shape. From A you go to B, then B, C, and D form a little cycle. B to C, C to D, and D back to B vertex is the only way in, and nothing points back to A. The method for powers is simple. For r squared, follow 2 arrows in a row. For r cubed, follow 3 arrows in a row. Let's do r squared first. To build r squared, we start at each vertex and take 2 arrows. Start at A, the first arrow takes us from A to B from B. The next arrow takes us to C, so in 2 steps we get from A to C, that gives the pair a C. Start at B, the first arrow takes us to C from C. The next arrow takes us to D, so we get the pair BD. Start at C, the first arrow takes us to D from D. The next arrow takes us back to B, so we get the pair CB. Start at D, the first arrow takes us to B from B. We go on to C, so we get the pair DC. The picture beside the table shows these 4 new arrows. That is r squared. Now r cubed. This time we take 3 arrows in a row. Start at A, we go to B, then B to C, then C to D, so we get the pair D. Start at B. We go B to C, then C to D, then D back to B. We end where we started, so we get the pair BB, a loop. Start at C, we go C to D, then D to B, then B to C again, we come home, so we get the pair CC. Start at D, we go D to B, then B to C, then C to D home again, so we get the pair DD. Look at the picture. 3 of the 4 vertices now have loops. That is because B, C, and D sit on a cycle of length 3. Now take 4 arrows in a row. Something nice happens. R to the 4th power comes out exactly equal to R. Why? Because B, C, and D sit on a cycle of length 3. 3 steps bring you back where you started. A 4th step then moves you on by 1, just as a single step would. Now the key idea behind all of this. The pair xy is in r to the power n exactly when there is a path of length n from x to y in r. That means you can walk from x to y using exactly n arrows, always following the direction of the arrows. So computing a power is nothing more than counting steps along the picture. Now we turn to a special kind of relation, called an equivalence relation. These relations sort the elements of a set into neat groups. This is the plan for this section. First, we learn what an equivalence relation is. Then we study equivalence classes, which are the groups it creates. At the end, we see how these classes split a set into pieces, which we call a partition. Now the main definition. A relation on a set A is an equivalence relation when it has all 3 properties at once. It must be reflexive, symmetric, and transitive. Reflexive means every element is related to itself. Symmetric means, if O is related to B, then B is related to A. Transitive means, if O is related to B and B is related to C, then A is related to C. If 2 elements A and B are related by such a relation, we say they are equivalent. We write a wavy line, then B. We read that as A is equivalent to B. Notice what this means for our work. Every test has 3 parts. If even one part fails, the relation is not an equivalence relation. Let's try an example with strings. A string is just a row of letters, like a word. We say A is related to B when the length of A equals the length of B. The length is the number of letters. So 2 strings are related when they have the same number of letters. Reflexive. The length of A equals the length of A. That is always true. So every string is related to itself. Symmetric. Suppose the length of A equals the length of B. Then the length of B equals the length of A, because equals reads the same both ways. Transitive. Suppose the length of A equals the length of B, and the length of B equals the length of C, then the length of A equals the length of C. All three hold, so this is an equivalence relation. Now a very important example, congruence. Mod m, let m be an integer bigger than 1. We work on the integers. We say A is related to B when A is congruent to B, mod m. What does congruent mean? It means m divides a minus b. In other words, a minus b is an exact multiple of m. We write that as a minus b equals k times m, where k is an integer. An integer matters here. K is allowed to be negative or 0. For example, take m equal 5. Then 17 is congruent to 2 because 17 minus 2 is 15 and 15 is 3 times 5. We claim this relation is an equivalence relation. So we must run the three checks, reflexive, symmetric, and transitive. We do the first two on the next slide. First, reflexive. Take any integer and work out a minus a. That is 0. And 0 is 0 times m, so m divides a minus a. That means a is congruent to a. Mod m, every integer is congruent to itself. Now symmetric. Assume a is congruent to b, mod m by the definition. That means a minus b equals k times m, for some integer k. Step 1. Multiply both sides by minus 1. On the left, a minus b becomes b minus a. On the right, k times m becomes minus k times m. Step 2. So b minus a is minus k times m, and minus k is still an integer, because flipping the sign of an integer gives an integer. So m divides b minus a, that means b is congruent to a. Mod m, the relation is symmetric. Last, transitive. Assume a is congruent to b and b is congruent to c, both mod m by the definition. A minus b equals k times m, and b minus c equals l times m. We want to say something about a minus c, so let's build it. Step 1. Write a minus c as a minus b, plus b minus c. The two b terms cancel, so this is the same number. This is the standard trick, add and subtract b. Step 2. Now replace each bracket using our assumptions. The first bracket is k times m, the second is l times m. Step 3. Add them. We get k plus l, all times m, and k plus l is an integer because adding two integers gives an integer. So m divides a minus c, which means it is congruent to c. All three properties hold. So congruence mod m is an equivalence relation on the integers. Now a warning example. Take the divides relation on the positive whole numbers. We say A is related to b when it divides b. Reflexive, does it divide a? Yes, A is a times 1, so every number divides itself. Symmetric, does it divides b force b divides a? No. The witness is 2 and 4. 2 divides 4 because 4 is 2 times 2, but 4 does not divide 2, so symmetry fails. Transitive. Suppose it divides b, so b is a times k, and suppose b divides c, so c is b times l. Put them together. C is a times k times l, so it divides c. Transitivity holds. So two of the three properties hold, but symmetry fails. One failure is enough. Divides is not an equivalence relation. Now let's group the elements. Let R be an equivalence relation on a set A. The equivalence class of A is the set of all elements related to A. We write it as a inside square brackets with a small r below. In symbols, it is the set of all S such that the para S is in R. In plain words, the class of A collects every element that the relation treats as the same as A. Any member of the class can stand for the whole class. We call such a member a representative. so the class does not depend on which member you name it after. We prove that soon. Let's see the classes for Congruence Mod 4. Each class holds all the numbers that leave the same remainder when you divide by 4. The class of 0 holds -8, -4, 0, 4, 8, and so on. These are the multiples of 4. The class of 1 holds -7, -3, 1, 5, 9, and so on. Each of these is a multiple of 4 plus 1. The class of 2 holds -6, -2, 2, 6, 10, and so on. And the class of 3 holds -5, -1, 3, 7, 11, and so on. Now look at the whole picture. Take any integer you like, divide by 4. The remainder is 0, 1, 2, or 3. So the number lands in exactly one of these 4 classes. The classes cover everything and they never overlap. Theorem 1. Let R be an equivalence relation on a set A. Take any 2 elements A and B. This theorem says 3 statements mean the same thing. Statement 1. A is related to B. Statement 2. The class of A equals the class of B. Statement 3. The class of A and the class of B share at least one element. Read the symbols carefully. They say the intersection is not empty. When we say the 3 are equivalent, we mean any one of them gives you the other 2. Let's prove one direction on the next slide. Let's prove that statement 1 gives statement 2. Assume A is related to B. Now pick any element C in the class of A and follow it. We start from what we know. C is in the class of A. Step 1. By the definition of the class, that means A is related to C. Step 2. We also know A is related to B. The relation is symmetric, so B is related to A. Now we have 2 facts. B related to A and A related to C. Step 3. The relation is transitive, so chain them. B is related to C. Step 4. By the definition of the class of B, that means C is in the class of B, and C was any element of the class of A, so the class of A sits inside the class of B. Now run the same argument starting from the class of B. It gives the class of B inside the class of A when each set is inside the other. They are equal. So the 2 classes are the same. The book proves the other 2 steps of the theorem. Now we define a partition. Think of cutting a set S into pieces. A partition of S is a group of subsets with 3 rules. First, no piece is empty. Every subset of sub I has something in it. Second, the pieces do not overlap. For 2 different pieces, their intersection is the empty set. Third, the pieces together cover all of S. The union of all the pieces equals S. Look at the picture. The big box is the set S. It is split into 9 cells, a sub 1 up to a sub 9. The cells do not overlap, and together they fill the whole box. That is a partition. Now why an equivalence relation makes a partition. Let R be an equivalence relation on a set A. Take any element A. It is always related to itself, because R is reflexive, so it sits in its own class. That means every element belongs to some class. Put together, the classes cover the whole set A. Now use Theorem 1. Any 2 classes are either exactly equal or completely separate. There is no partial overlap, so the classes are disjoint pieces that cover A. That is exactly what a partition is. Each colored block in the strip stands for one class. Theorem 2 ties the 2 ideas together, and it works in both directions. First direction, start with an equivalence relation. Its classes form a partition of the set. We just saw why. Second direction, the converse. Start with any partition, a group of disjoint pieces. From it, we can build an equivalence relation whose classes are exactly those pieces. So equivalence relations and partitions are really the same thing, seen from two sides. Give me one, and I can give you the other. Let's prove the converse on the next slide. Now the proof of the converse. We start from a partition and we build a relation. The rule is, x is related to y when x and y lie in the same piece. Reflexive. Take any element A, it is certainly in the same piece as itself. So the pair is in R. Symmetric. Suppose O and B are in the same piece. Then B and R are in that same piece too. Sharing the piece does not care about order. So the pair BA is in R. Transitive. Suppose O and B share a piece and B and C share a piece. Then B belongs to both pieces. But the pieces of a partition are disjoint. Two pieces that share an element must be the very same piece. So O and C are in it as well, and the pair of C is in R. One step is left, and it is easy to skip. We must show the classes really are the pieces. Take an element A and let a sub I be its piece. An element X is in the class of exactly when X shares a piece with A. The only piece it belongs to is a sub I, so that says X is in a sub I, the class of it is a sub I. So R is an equivalence relation, and its classes are exactly the pieces we started with. Now we turn to a new topic, partial orderings. This is a special kind of relation. It captures the idea of ordering things, like less than or equal to, or one set inside another. This is the plan for this section. First, partial orderings in the sets they act on called posets. Then lexicographic ordering, which is dictionary order. Then Hasse diagrams, which are neat pictures of an order. Lattices are not in these slides yet. And topological sorting is not in these slides yet either. Let's begin. Now the main definition. A relation R on a set S is a partial ordering when it has three properties. It is reflexive. Every element relates to itself. It is antisymmetric. If A relates to B and B relates to A, then A and B are the same. And it is transitive. If A relates to B and B relates to C, then A relates to C. When a set S carries such an order R, we call the pair a partially ordered set, or a poset for short. We write it as S with R. The members of S are the elements of the poset. Compare this with an equivalence relation. Two of the three tests are the same, only the middle one changes. An equivalence relation is symmetric. A partial ordering is antisymmetric. That one swap changes everything. Instead of grouping things together, it ranks them. And the word partial matters. Some pairs may not be ranked against each other at all. We come back to that. Let's check a first example. Take the relation greater than or equal to on the integers. Reflexive. Is every integer greater than or equal to itself? Yes, because equal is allowed. So is greater than or equal to A. Antisymmetric. Suppose A is greater than or equal to B, and B is greater than or equal to A, then neither one is strictly bigger, so A and B must be equal. Transitive. Suppose it is greater than or equal to B, and B is greater than or equal to C, then A is greater than or equal to C. All three hold. So greater than or equal to is a partial ordering. These facts come from the order axioms for the integers. Now a second example. Take the divides relation on the positive integers. Reflexive. Does a divide A? Yes, because A is a times 1. Antisymmetric. Suppose A divides B and B divides A with both positive. then A is at most B, and B is at most A, so A and B are equal. Transitive. Suppose A divides B, so B is a times K and B divides C. So C is B times L, then C is a times K times L, so it divides C. All three hold. So the positive integers with the divides relation form a poset. Look back a moment. Earlier we saw that divides is not an equivalence relation because it is not symmetric. That very failure is what makes it a good ordering. It is antisymmetric instead. Now a third example. Take the subset relation on the power set of a set, as the power set is the collection of all subsets of S. Reflexive. Is every set a subset of itself? Yes. Every element of A is an element of A. Antisymmetric. Suppose A is a subset of B, and B is a subset of A, then the two sets have exactly the same elements, so they are equal. This is the standard way we prove two sets are equal. Transitive. Suppose O is a subset of B, and B is a subset of C. Take any element of A, it is in B. So it is in C, so A is a subset of C. All three hold, so set inclusion is a partial ordering. Now we compare elements in a poset. We write the order symbol as a curly less than or equal to. It just names the order in whatever poset we are looking at. Definition 2. Two elements A and B are comparable if A comes before B in the order, or B comes before A if neither holds. We say A and B are incomparable. That is why we call it a partial order. Some elements simply cannot be placed against each other. For example, under divides, 2 and 3 are incomparable. Definition 3. If every pair of elements is comparable, we call the set totally ordered or linearly ordered. The order is a total order, and the set is also called a chain. Definition 4. The set is well ordered if it is totally ordered, and on top of that, every non-empty subset has a least element, a smallest one. Lexicographic order is dictionary order. Start with two posets, a 1 with its order and a 2 with its order. We want to order the pairs in a 1 cross a 2. We say the pair a 1, a 2 comes before the pair B1, B2 in one of two cases. Case 1. A 1 comes before B1 in the first order. Case 2. A 1 equals B1 and a 2 comes before B2 in the second order. So the recipe is simple. Compare the first parts first. If they tie, and only then, compare the second parts. This same idea extends to strings. Compare letter by letter from the left until the letters differ. Let's work two comparisons the way a dictionary does. First, discrete against discrete. Walk the letters together from the left. D, I, S, C, R, E. The first 6 letters are the same. Now the 7th letter. In discrete it is E, in discrete it is T, and E comes before T in the alphabet. So discrete comes before discrete. We stop there. The rest of the word does not matter. Second, discrete against discreteness. Walk the letters again. The first 8 letters agree. D, I, S, C, R, E, E, T. Now discrete has run out of letters while discreteness carries on. When one string runs out first, it comes first. So discrete comes before discreteness. So there are only 2 rules. At the first place the strings differ, the smaller letter wins. And if one string simply runs out, that one comes first. A Hasse diagram is a clean picture of a partial ordering. The idea is to hide the edges we can work out anyway. We hide the loops because the reflexive rule says every vertex has one, and we hide the edges forced by the transitive rule, the long jumps. We will build one now. The order is the chain on the numbers 1, 2, 3, 4, where 1 comes before 2, 2 comes before 3, and 3 comes before 4. We start from the full picture with every loop and every order edge drawn. Then we take things away, step by step. Look at the 3 panels from left to right. Panel A shows the full order. Every number has a loop back to itself from the reflexive rule, and every order edge is drawn, including the long jumps, 1 to 3, 1 to 4, and 2 to 4. Panel B removes the loops. We know they are there, so we do not need to draw them. The long jumps are still in the picture. Panel C removes the long jumps as well. Why can we? Because transitivity puts them back for us. If 1 goes to 2 and 2 goes to 3, then 1 to 3 follows on its own. What is left is a simple vertical chain. 1 at the bottom, then 2, then 3, then 4 at the top. We also drop the arrowheads because every edge now points upward. That last picture is the Hasse diagram. Now the recipe to build a Hasse diagram. Begin with the full directed graph of the order. Then do 3 steps. Step 1. Remove the loops. Every vertex has 1 from the reflexive rule, so nothing is lost by erasing them all. Step 2. Remove the transitive edges. If there is an element z sitting strictly between x and y, then the edge from x to y is forced by transitivity. Erase it. Step 3. Place each edge so the starting vertex sits below the ending vertex. Now every edge points upward, so we can safely remove the arrowheads because the direction is clear from the picture. What remains is the Hasse diagram, the smallest picture that still carries the whole order.